I'm going to continue with the discussion of drawing electric field lines, but this time I'm going to do it for a negative charge rather than a positive charge. So I'll draw it as a black dot rather than a red dot. And remember, the electric field lines describe to us the direction of the electric field associated with a given charge configuration. In this case, it's for a single charge and a single negative charge. We already talked about the case for a single positive charge, and in that case, the field lines radiated away from the charge. But for a negative charge, the field lines, and I'll draw them in blue just so that I can distinguish them from the negative charge, they will be directed toward the charge. So if I were going to draw it, it would look something like this. And of course, the larger the charge, the more field lines I would then draw within the circumference to reflect the fact that the electric field is going to be stronger. And that is evidenced by the greater density of field lines that are present in here. So in this case, you would argue that the electric field that I'm drawing is going to be stronger than it was in the case that I had just drawn, because the density is so much greater of the field lines at any point, at any distance away from the charge. Of course, as I get further and further away from the charge, the density of field lines goes down, so the electric field is weaker further away from the charge, which is consistent with what we've been discussing. So this is how we would draw the electric field line configuration for a single negative charge. It looks very similar to that of a single positive charge, except all the field lines are pointed inward. Now I want to do one more example, but I want to have both a positive and a negative charge. And this is something you have seen in this class a little bit already and in your chemistry class, maybe even other classes as well. This is something we call, if the charges are the same size, so if I call this one minus Q, and if I call this one other one up here plus Q, we call this a dipole. That's what this is. So how would I draw the electric field lines for a dipole? I'm not questioning that it's a dipole, I'm just questioning how to draw the electric field lines for it. Well, by definition, the electric field lines, always leave a positive charge and they go to a negative charge. So one of the field lines would go like this for the dipole. First, I have to say, too, I have to define how many field lines would be represented by a given charge. So let me just call this one, I'll put a number here. I'll say that this charge here is plus 1 microcoulomb. And I'll call this one down here minus 1 microcoulomb. And I'll say that we have, this number is rather arbitrary, but I could say 5 lines per microcoulomb. Clean up that M. What that means then is that there should be 5 lines leaving this charge here and they're actually leaving, but they're eventually coming around here. You can't see them because they're so extensive they leave the screen. But you can see I have 5 lines up here and I have 5 lines down here. So both of those conditions are satisfied. These lines are all pointed away from the charge, as they should be, because it's a positive charge up here. This one down here is the negative charge, so all of the lines, the electric field lines, should be pointed toward the negative charge. Okay? So in this video, you saw the electric field line configuration associated with a single charge particle, and in this case you saw it with a dipole, 2 charges of the same sign. We could draw it for any kind of charge configuration, as long as we follow whatever rules we set up for the number of lines we want to draw per microcoulomb. And I'll just draw another case here. Let's just say rather than 5 lines per microcoulomb, I said, oh, actually, well, I'll keep it 5 lines per microcoulomb, but let me just do one more case here, and then I'll call this video done. Let's say I have, rather than 1 microcoulomb, let's say I have 2 microcoulombs. So this would be negative 2 microcoulombs. This would be positive 2 microcoulombs, let's say. All right, and let's draw the field configuration for that. Well, I've already got half of it done. But since there's 2 microcoulombs here, and I'm going by the 5 lines per microcoulomb, I have to draw a total of 10 lines associated with this guy. So I'm at, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So I need 2 more, and I could say, good, there's one there, there's another one here, there's one there, and there's another one here. Now they each have 10 lines, either leaving them or coming towards them. And this is almost looks like a pumpkin in there, but that's just the way the lines, the shape of the lines go. But what we could ask then is, where's the electric field strongest? Well, it's going to be strongest close to the charge here, where the density is greater. It's also going to be really strong here. Near both charges, it's going to be strong. You're going to have a strong electric field. All right. So this is the example of a dipole, but with twice the charge, as I showed you in the previous case, and what the electric field configuration would look like for that dipole. All right, enough for this video.